Dear world, welcome back to this session of Trie. So this is actually Trie, which is also called Prefix Tree. So in this session, we'll be starting the Prefix Tree, and then first we'll be studying that why do we need Trie. First we'll be studying, let me just mark it. First we'll be studying why do we need Trie. Second, we will be studying what are tries. That means why do we learn try? Why will we be learning try? First, we will know the reason. Then second, we'll know what actually is try. What is the definition of try? What do we understand from the try? So we'll be understanding the tries. Second and the third. After that, we will be observing all the methods of try. That is insert method, search method, and delete method. These are the three most prominent and important method in try, and these are very useful for solving any lead code problem, DSA problems, on any problem like CodeChef or HackerRank. So third, this is. Then we'll be discussing the time and space complexity. I mean, if you are a DSA problem solver, you know the importance of time complexity. So then we will be discussing the time complexity and drawback of standard try, and then we'll be discussing the drawback that we applied the try but it has some setbacks, it has some limitations because of why it failed and another data structures came to the role. So we'll observe the drawback also. So this is prefix try. Before we observe, we are actually a programmer, so we should first observe the code. Now I will show you by running the code that how it's working, and then we will understand the concepts, we will understand the entire concept, and then again we will implement the entire code. So first, after running, we'll be deleting the code. So let's move to the code section. Then we'll again come back to this theory section and we will be observing the entire theory. Okay, so I have already come to the code section. Look, this is the Java strings algorithm playlist, and I have been making video on strings algorithm. So first we have observed the manager's algorithm, then I have been making video on all the algorithms, and now right now we are in tries. So in today's video we will be observing try. In next session we will take try to the compressed try, then we will take it to the suffix try, then again we will elevate it to the ternary search trees. So this way we will be elevating cells. So let's run the code. Look the code. First, this is try, where we are implementing the actual try class. This is try class, and here we have implemented all the method. You can observe we have implemented the insert method. One of the most preeminent, very important method is insert method. Then we have implemented the search method of try, through what we can search the element that we have inserted. And then we have also, this is start with, this is a prefix method, through what we can search prefix, like some pattern finding prefix or some substring type of problems in DSA we can solve with the help of this. And for that we have used the try node, our self-made node. Now look, the most important thing in try node, that here there is boolean is end of string. We have used one data boolean is end of string in try. One thing is boolean is end of string, and the second thing is we have used pointers. Observe here, try node children new try node. This is what? This is array of pointers. Look this mark. This mark, if you just observe this mark, then just get it that is the array. And look the data type. This is try node is the data type. That means all the children will be pointers, and here we have initialized them to null. So we will come back to the entire section later after understanding the theory, but for now we will run the code because we are programmer. We don't understand just by concept, we understand by practical analysis and running the code. So let's run the code. This is try, and we will be running the file. So first look, this file try is inside the folder try is. So we have to change the directory, cd change directory, try is. Okay, and now we'll be running the file. Before running, we need to compile the file. Java compile -d dot try dot java. Okay, it got compiled. Java try dot java try, and it will run. Now look, first we inserted apple and app, that got inserted. Now as we have inserted apple, it should return true. It should return true app also. So it has returned the value. That means we saw that our code is working. The code we are going to implement is working. Now let's move to the theory section and let's understand the all theory about the trie. So welcome back to the theory section. Okay, so first understand, this is look the side, the picture in my right side. Can you observe the picture in right side? Yeah, look, this is what is the actual structure type of trie. This is how we represent the trie. That first, in data structure, trie is represented, there will be first a root, okay, and then we insert trie one by one. We insert in trie, we always insert one character by one character, then one character. So this is how we insert the trie. So we got an idea, then we came to the left side, we came to the right side, we can go to the more sides, the more we want. So before that, let's understand one by one the factors that why do you need trie. Why do you need trie? Suppose while solving mainly pattern type of problem, pattern searching problem, what do I have observed? Let's take a text. Let's take a text. The text is A, B, C, D, E, F, and let's take a pattern. Let's say a pattern. And let's say a pattern that is ABD. Okay, now let's tell a pattern ABD. So how would we actually be searching the pattern? Look, first, if we just use the normal approach that we already know, we all know, so what we will be observing, we'll be using the normal method to compare to the patterns. So first we will take this size of window and we will compare with this. They are not matching, so we'll again move to this. Again they are not matching, so again we'll move in that side. Again they are not matching, so we'll again move to that side. So after this we will stop. That means here we are moving. If we call this length, let's tell the length to be n, the length of the text was telling n and the pattern to be m. So as per we will be comparing here for n minus m plus 1 times. For how many times we will be comparing? N minus m plus 1 times we will be comparing. Now look, in pattern there is m length, so after if suppose they match, there is ABD, that's why they are not matching. So let's change our pattern. Suppose our pattern is let's say our pattern is DEF. Got it, our pattern is DEF. And now if we come in this iteration, DEF, we see that our pattern is being matched. We can see that our pattern is being matched. Then what we will do, after this we'll compare one by one. We'll compare this D with this D, we'll compare this C with this C, we'll compare this F with this F. That means first we'll be comparing for n minus n plus 1 times, and then we'll be comparing for all the letters that is in our pattern. That means our total time complexity will be that will be m into n minus m plus 1. So if we just multiply it, we get big of n square time complexity, big of n square. So that is mn, we are not moving into that, but we are getting that the time complexity here is coming is big of n square, and this is a very long time complexity. And what is the main reason behind DSA algorithms is we try to reduce, we always try to reduce the time complexity. We try to reduce the time complexity. We try to reduce the time complexity. We try to reduce the time complexity. That means our main goal is to trying to reduce the time complexity. We got the time complexity to be big of n square, but what we want some method where we can use the time complexity of big of n. That means what? We want to come in the linear time. We want to come in the linear time. Linear time. So, are you observing that we got the time complexity big of n square using the brute force method? Here we have applied the brute force method. That means we are comparing one by one and for all, then at the end we are comparing. This is called brute force method. That means trying all possible combinations. Now let's understand. If we apply another type of method here like Manacher's algorithm, so we get some time complexity like big of m plus n. Big O of m plus n. We get that type of complexity. So here also comes that m plus n, that means pattern length plus text length, pattern length plus text length. We get pattern length plus text length. So we get pattern length plus text length. That is what we get. That means here this is also becoming large. That pattern length plus text length, that m plus n, this is also becoming large. We want to reduce it more. We want it that why do we want to get such much large? A, B, C, D, E, F, and there is D, F. Why will we will be taking so much of time and space complexity? Why not? Or we will try to reduce it in more way that we only have to do for this DEF. That means we will try to come to in such a method where our time complexity reduces to only this length, that is 3, which is we are telling here m. So we want a method where this time complexity reduces to big of m, that is only up to equal to the value of pattern. And when we come to we want to reduce in such a level, then trie comes in the rule. Then we come to the trie, then trie plays in the rule. That means we use trie. Why do we need trie? So to use the method where our time complexity reduces to only up to the length of the pattern, big of pattern, we use trie. This is why we use trie. Now the second question. First question is the resolve. Why do we need trie? So we want a method from where the time complexity reduces from big of n squared to big of n to big of m. That means from text, this big of n can be text and this is pattern. That means we want to reduce our time complexity to the least possible. That's why we use trie, and to come in the pattern we have to use tries. Any type of tries method, but we'll be starting from using the tries. That's why we need trie. Okay, this is the result. Now second, what are tries? You can observe the what is tries in the figure. Look, what can you observe in the figure? Just observe the figure, that it is actually a tree-like structure. Tries is actually a tree-like structure. That is tries. How we store the elements? Let's move to the theory. Prefix trie. Okay, I came to the theory portion. A trie also known as a prefix tree. As I told you that a trie is also known as a prefix tree. Is a tree-like structure. This is a tree-like structure that stores strings in a way that allows for efficient retrieval, insertion and search of string. Efficient retrieval, that means what? Efficient, the word efficient, that means it will use the least possible time. That means it is one of the most optimized method, especially when dealing with large number of words. Dealing with large number of words, that means what? Just imagine you have a dictionary and just guess how many words will be in dictionary. It might be up to 1 lakh. It might be that there is 1 lakh of words. So you want to search very quickly. In that case, we will be using the method trie. Just think there is 1 lakh words and you want to search a pattern. Say my name Farhad. We want to search a pattern Farhad. So if we just use any other type of optimized algorithms like Farhad for that, and it will be the time complexity will be big of 1 lakh. So what is this? There is only 6 Farhad, there is only 6 letter and we are using big of 1 lakh. This is not optimized. So we want to use big O of only 6, and that's why we use try. So this is using for dealing with large number of words of sequences, and if there is sequences, that means pattern type. This is why we use try. Tries are commonly used for tasks like autocomplete. Like autocomplete, for autocomplete, we have seen in the Google that there is autocomplete system for spell checking. That means for spelling checking and prefix based searches. Prefix based searches. Okay, let me tell you first. Prefix based. You might not have a proper idea of prefix. Okay, let me tell you the what is prefix. Let's erase it. Okay, prefix. The word prefix. Observe this prefix. So you don't suppose let's take a name Farhad, and so let's take a name programming. So what do we call prefix? If we take this as a word, then we can call a prefix to all the word, we can call it a prefix. That means if anything, any substring that starts from the beginning, if anything that starts from the beginning, then we can call it a prefix. That means programming is a prefix. If we just tell programming, G is not here, then this is also a prefix. If you call it programming, this is also a prefix. Dot 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 dot, if you call it PRO, this is also a prefix. P is also a prefix. That means if it starts from the beginning, and goes sequentially up to any length, then we call prefix. So this is also used for prefix based searches. Okay, so key concept of trie. Let's study those nodes. Each node in a trie represent a single character of a string. Each node, look what we have observed there in the above figure photo. Let's take a example here. Again we are taking an example, let's say code. So how we represent code in a trie? First there will be a root node. This is a root, and then there will be C. Then after C there will be O, then after this there will be D, and then thereafter this there will be E. So this is how it's represented. That's how it's represented. So each node in a trie represent a single character of string. This is representing a single character, this is representing single character, that is also representing a single character. So these are representing a single character. Root, the topmost node is root. This is the topmost. This topmost node is called the root, which does not store any character. Look, it does not store any character, so we have renamed it root, and there is no any character. It's just the starting point of the trie. It is the starting point from where the trie have started. Prefix trie. Now we will be starting this prefix trie. There is a term called children. Let's understand what children. Each node has an array of children where each child corresponds to a character in the alphabet. Look this, understand. Here we have got the node. Now we'll be analyzing this C. We'll be analyzing this C. Let's understand this C. So if you analyze, this is a node. What it actually contains? It actually contains a character. It contains a character, number one, and number two, it contains children. You might be thinking, children of what? Children of pointers. Children of what? Children of pointers. So it actually contains an array. This is array of children. Array of children. So the actual structure of it will be like this: character C, and there is a long array of, let's say, 26. Look, if we are using small case English letters, then we will be taking 26. And if suppose you are working for a trie where you are storing all the symbols, then you will go for all the ASCII character 256. You will move for all the ASCII character 256. So this is character. So this is actually the node looks like. So that is the structure of actual node, that there is one character C and there is one array. So that is told here. that each node has an array or map of children where each child corresponds to a character in the alphabet. Look, each child corresponds to a character in the alphabet. Okay. End of word marker. A boolean value is stored at each node to indicate whether the node represents the end of a valid word. And not only this, here also we use a boolean value. That means is end of string. We use a boolean value this type of is end of string. So this is end of string is boolean value and it actually stores either true or false. It stores either true or false. So this is how what is actual structure of a node. So if we conclude the actual structure of a node that we got, this is the root. First the structure we got, that is the root. We got root, and the root doesn't contain any element. It doesn't contain any character, it doesn't contain any array, it doesn't contain any boolean value is end of a string. Now after this, if here our element c comes, see this is a node and this is a structure. After this, let's say o comes, this is a structure. After say let's, it contains d, this is the structure of d. So this is CODE. It contains D, E. So first it contains a character. Second, what it contains, a array of pointers. A array of pointers it contains. And third, what it contains, a boolean value. Is end of string. Is end of string. That will be value either true or false. Either true or false. So this is the actual structure prefix. So for all that will be the same. It also contains a array and a is end of string. Is end of string. It also contains a array and it also contains the same is end of string boolean value. So this is the actual structure of trie. So prefix trie, why do you need trie? We have understood this. What are tries? We have also understood this. Now insert search delete operations on trie. Okay, we'll be observing this, and then time and space completion and drawback of standard trie. Till now we have observed the end of word marker is end of string. In our code we have used the word marker as is end of string. Is end of string. Is end of string. We have used this as word character. Or I have used like is end of word. So anything that you can use in your code, that is your choice, but that is what I have used in my code. Okay, so operations on a trie. Insertion. We will be observing the insertion operation, how the elements are inserted first theoretically, then we will observe in the code. Search operations, prefix search and deletion. Okay, so first let's move to the above, where already we have one elements. Look this, prefix tree. Here we are inserting bad, batch, better. Try to observe it. Bad, batch, better. So first we have taken as root, as I told, then we have taken the letter from bad, we have taken the letter B, we have inserted B. After we have inserted B, look, first what do we need to take? We need to take a root. We took a root. After root we took a letter B. There is letter B, but keep in mind there is character B we are representing, but this B character is also having an array. This is also having an array, and also the flag is end of string or is end of word. This is also having this. This is also having an array. And also the is end of word. Is end of word. This T is also having this array. They all are having this array. So first we took this boolean B. After there is A, so we will be inserting A. After there is T, we will be inserting T. Now look, we have inserted the word bat, so we are marking as done. Now try to observe the next word batch, BATCH. Now while we insert the second word, we will start again from the root. We will come in the root, that means our current node pointer. Our pointer, let's say the current node. Let's say here there is our pointer current node. our pointer current node. Here is our pointer current node. It will again start from the root. Our pointer current node will again start from the root. Now it will check the first letter B, if there is B or not. Yes, there is B, so it got inserted. Pointer will come here. It will again check if there is A or not. Yes, there is A. Look, there is A. So A got inserted, the pointer will come here. It will again check if there is T or not. Yes, there is T. So it again got inserted. Now it has inserted the BAT. Now look, the fourth character C. While it will search for C, if there is any C, look now the T, it has also an array. It has a long array and it will search in array that if there is T, be it if there is C. So it will observe in this array that there is no C in this array. There is no C in that array that I have drawn. In here there is no C. So what it will do, now it will insert the element. Now it will insert the element. So there is BAT, so it will insert a new element C. So it will insert element. Let's say we are inserting this side. Now you will understand in which side we have to take. Look, there is C and T, so we are inserting just casually C. Okay, now H. Again the pointer will come here and it will again check if in the C, in this pointer, if there is already H and H is not there because we have not already inserted the H, so it will insert the H. Okay, then it inserted. Now our pointer will come here. As the pointer came here, there is nothing, so okay, this and word is finished and the loop is done. Now for the second, now again for the third word, better, BATTER, BATTER. Look, now again for this word our pointer will again start from this beginning, from this root. Then again it will check B, yes, matched. Then it will come to the next one, A, yes, matched. Then it will come to the next T, yes, matched. Now it will check for T again. Now look, now the current pointer is here in this T, and this T, this middle T is also having its own long array of 26 characters, long array, and it will check here if there is T. No, here is C, A, B, C. So there is not B also, here is only C. Because we have inserted C, we have not inserted. So here is only C, there is not the T. So what it will do, now it will insert an element. It will insert that element in this side. Why in this side? It will actually insert it according to their value. C is less than T. This C is less than T, so it will take left side, and T is greater than that type, so it will take right side. So this is better. Now it came here. It will again check for it in this array. The pointer will come here. If there is E, we haven't inserted E, so it will insert E and then it will insert R. So this is how elements are inserted in Trie. So this was the first example. Let's insert this cat and car. So first we will take a root node. First we will take a root node. Root. Root. Okay, now we are trying to insert cat. So after root there is no element, so we are inserting cat directly. This is a cat. So this is done. Now we will check its array if there is already A or not. There is not A, so we will insert A. If there is T or not, there is not T, so we will insert T. If there was any letter already existing, then we would ignore that one. Here insertion is done. Here insertion is done. Insertion is done. Insertion done. Insertion done. In T, here also insertion is done. Insertion is done. Now look, cat is done. Now come to the second example of car. Now while we insert car, we again start from the root, then we'll come to the C. Now look, observe, here C is already inserted, so we will not insert here. We will just ignore. We will just bring the pointer to next. Not insertion, no insertion. We just brought the pointer to next. It will again come here, already inserted, so it will come to the next. Now it will check in the A, it will check for if R is existing here. there is no R, so it will take to the PQR so there is, so R will take to this side and the R will get inserted to that side. This is how the insertion is done in prefix tree. Let's check another example. Banana. So this is banana, BANANA. It will start, this is the root, and from root it will start from there. For the letter B, look, for the letter B, here in the root, this is pointing to the root current node. Now we'll be inserting the letter B because it doesn't exist, so inserted. Now after inserting, it has also an array. Now the pointer will check if there is already a pointing somewhere here, but no, nothing is being pointed because we haven't inserted. So it will insert A, then it will insert N, then it will insert A, then it will insert N, then it will insert A. All those inserted. Now in case of band, the second letter band, it will check here if there is already A. Yes, there is already A. So it will not insert now. No insertion. It will just come down. Now it will again check if there is N. Yes, there is N. It will just come down. Now it will check if there is D. Now in this array there is no D. So it will insert the D. Now the insertion will happen here. In this section the insertion is done only. Okay, there are more examples and you can practice all those. So this is all the things about prefix tree. So we will be forming the entire trie. So let's move to the code section. Okay, let's delete the files. So I just deleted all the files. Okay, so first to create the trie we need two things. First we need the trie node, because trie class is constructed of nodes. You know the special data types that are declared. Just have again loop. What is that? Look, those nodes, these are all the per pixel, these are all the nodes. So these nodes have a particular structure. We need to define those nodes. That means first we need to make a data structure for those nodes. So this is called trie node. These are all trie node and we will make data structure for this trie node. So first we will make a Java file for this trie node. Code trie node.java, public class trie node. Okay, so we have declared the file. In file we had to first declare the character place. So we will declare in such a way that we will actually store the pointers and the boolean is end of word. So let's declare the arrays. Trie node. Look, now we are declaring our array. Trie node children, that is new trie node of 26. Here trie node, this is the data type of the array children. This is array, that means we are constructing an array of children. So this is 26. You might be thinking why 26? Because we are assuming using only small case English letters A to Z. So this is trie node children. Now we'll be using boolean is end of word or string, whatever is the end of word, false. So by default we are using false. Now we will be initializing all the pointers. That here all the children, that means there is this is our array, and now we'll be initializing the values of array. So for that we will be using constructor trie node for integer I equals to 0, I less than 26, I plus plus. children of I equals to null. So here all the pointers are pointing to null. These are all the pointers, that means what points to the data and I mean nodes that I observed in. So this is, we have already made the trie node data. Now we need to make the main file trie. So let's make code trie.java. Okay, so here we'll be implementing the insert method, search method and prefix method. And for that, let's make the file public class trie. First we'll be declare a pointer private trie node root. So this is a pointer reference to our main trie node class where we have made the class. That means this trie node, this root is pointing to this node. This is just a pointer, it has not been initialized. That is just a pointer and we will initialize that pointer by using a constructor public trie. So this is, we are using default constructor public trie root equals to new trie node. Okay, so using the root equals to new trie node, now we have initialized. Look, here we have just declared the pointer a reference, basically here root new trie node. This is initializing the node. So now this is pointing to new trie node, it is actually pointing to new trie node. Now we'll start inserting method to insert a word into the trie, method to insert a word into the trie, public void insert string word. So trie node, look, we have talked there about our current node, so we will be using the current node here. So let's use current node. Actually current is not a node, it is actually a pointer to the current node. So this is, just name it trie node current equals to root. So currently it will point to the root. If I show you in the diagram how this is working, we are just doing this section. Look, here our pointer does what? Points. So first here there was our pointer, now this pointer is here, now this pointer will come here, now this pointer will come here. So what we have done in this section, that we have just initialized. When we have initialized this pointer first time, observe this line public trie node root. So this is just a pointer root, and it is not pointing to anyone, that is just like pointer. After that we have initialized, then it was pointing to a node after we have initialized. And now look, trie node current equals to now node, we have again initialized one more pointer current, so now it is pointing to the root. So this is current, current. So we are talking about this current pointer. So we were actually talking about this current pointer, what is being pointing to root. Okay, so let's focus on the code section. Public trie node current equals to root. Now let's start. For character C, as we insert one by one, word dot to character array, First we need to find the index, integer index equals to C minus A. Using this we will be finding index. You might be thinking how we will be finding the index. So I think A is having ASCII value of 65, and if A is having ASCII value of 65, then C will have ASCII value of 66, 67. It will have an ASCII value of 67, that is equals to 2. It will automatically take the value 2. That means A will take the value 0, B will take the value 1, and C will take the value 2. So we are assigning in this section because we have only 26 arrays, 26, so we'll assign them from 0 to 25 section, 0 to 25. That's why integer index equals to C minus A. Now we'll be check if current dot children of index equals to null. If this is null, that means there is no element, so we'll be initializing current node, current dot children of index equals to new trie node. Okay, now we have declared here one node. Now we will be updating the current dot children so that it points to the next element to bring it down. Current dot children of index. Now it will work for all the letters in that for loop, and after that all characters has entered, we will mark the last node as the end of the word as true. Look, we have used a variable is end of word. Now as soon as the loop is terminated, this is in end of the word becomes true, so we'll mark as true. Current dot is end of word equals to true. So now we have successfully inserted a word. So this was the method to insert a word into the trie. Now we'll be using a method. Now we'll be implementing the search method for a word in the trie. Method to search a word into the trie. So public boolean search string word. Okay, we will again use the same things. Trie node current equals to root for character C in word dot to character array. Integer index equals to, the same concept is here, so I'm not explaining. C minus A. If current dot children of index, if current dot children equals to null, that means element doesn't exist, so we will be returning false. Okay, now we will be bringing the cursor to the down. Current equals to current dot children of index. It will keep searching for all the characters. After the loop ends, will be return current dot is end of word. So whatever the value of word will be true or false, it will get returned, and this is how we can search the method. Now we'll be implementing the method to check for prefixes. Method to check if a prefix exists in the tree. Method to check if a prefix exists in the trie. Public boolean starts with string prefix. Trie node current equals to root. Again it will start from root, as we are assigning it to root. The address of root is being assigned, so again current will point to the root. For similarly for character C in word dot to character array. For character C in word dot to character array, integer index equals to C minus A. So we got the index. Now we'll be check for if current dot children of index. If this is equals to null, that means here the pattern is not existing, so we will directly return false. Pattern of prefix do not exist. Now we will be bringing the pointer current to the next current dot children of index. Okay, and now after all searches are done for the for loop, we can return true. That means if for all the pattern search is matched, that means the pattern was found. All characters of the prefix exists, so returning true. So we can check the method also. Let's run the file. Java compile -t dot trie dot java. For character C cannot find symbol, line number 36. For character seen what, sorry, here we have taken the argument as prefix, so we have to give prefix dot to character array. So again let's run java compile, and now java try, but we haven't implemented the main method till, so we have to implement the main method, then only we'll be able to observe other things. Public static void main string of try that is equals to new try. Okay, so we have instantiated object, this try is the object, and now we'll be inserting words. So let's insert try dot insert apple, try dot insert app, try dot insert mango. Okay, we have inserted those. Now we will be search should return us true. Look, searching words, try dot search, and apple, we have inserted the word apple, so it should return us true. Try dot search apple mobile, it should return false because we haven't inserted the words. Okay, after that let's try checking the prefix. Try dot starts with try dot, it will also return us true or false, so try dot start with man, because we have inserted man, so it should return us true. We have to print all those methods only, then it will return. So let's try wrapping all those. System dot out dot print ln. Okay, now they will be printing. Now let's again compile java compile, java try, and now you can see true, that means we got the true. False, this doesn't exist. Man, this prefix found. So this is how our try works in the time complexity of big of n. So we have implemented the method, and it's actually 1:18 p.m. of night. Yeah, it's 1:18 p.m. so I just started with the video. I don't know how the quality was, because tries are little bit tough tough algorithm, so yeah, it was also confusing for me. Okay, so in the next lesson we will understand the try, because this try is having few drawbacks. Okay, let me tell you the drawbacks. Let's move to the tab. Okay, we have come to the tab, and prefix tree, insert time and space complexity. So look, phone number, this is time and space complexity. So whenever we work in try, so it has a time complexity. If we talk about the time complexity, here we only look the word, that means we only look the pattern. So here the time complexity, that will be big of pattern length, pattern or odd length, whatever the length that is, that means this got reduced to big of n, which you wanted. From big of n square, it got returned to big of n, and now this is big of m. This was text, so we reduced it into pattern length, so we observed something. So this is the time complexity. What about space complexity? Time complexity got reduced to big of pattern or odd, whatever length. Okay, but the space complexity, observe, whenever we are inserting, this is a root, we are inserting any element C, A, T, so we are inserting here cat, cat. We inserted cat here. So for every letter we are inserting 26 character, 26 pointers there are. So this is when we are only assuming of 26 A to Z small case. What about if we just assume all the 256 ASCII character? If you assume all the 256, then this length will be 256. That means then the space complexity will be 26 star word length, word or pattern length. That means this amount would be our space complexity, that is 26 times or 256 times. And if the word length is higher, here the memory consumption will be higher. So why to use so much when there is only one? We will be using only one. Why to waste so much space? So this is the drawback of the trie, that we are wasting memory. We want to save this memory also. And for this, the next topic came into the play, that is compressed trie. Compressed trie. So how compressed trie remove this, we will be observing in the next lecture. Compressed trie. So we are finishing this lecture here. So that was all about prefix trie. We saw the time complexity, we saw everything. We even implemented the code. So the problem we got with space, that we are using long prefixes, and that was wasting the memory space. So to save the memory space, we adopted compressed trie. So let's meet in the next session on compressed trie. Thank you. That's all for attending the session.